Hello again. Here we are. I've got lesson 4 this time. I'm going to be looking at some telescopes. Last time we looked at the Rayleigh criterion, which is one way of being able to classify and evaluate a type of telescope and see how good it is, see if we can see some objects. But this time we're going to be looking at where to put a telescope, size of it as well, and also a little bit on how they work in terms of the CCD, charge coupled device. That's what it says there in the middle of the specification. The charge coupled device is the key to all telescopes and what's made them fantastic over the last 50 years, I suppose, when they first started being used. We'll come up with some brand new terms as well. We've looked at angular resolution, we've looked at Rayleigh criterion. Radian I am going to touch on for very small amounts. You can look elsewhere to see what radian is, but then the idea of quantum efficiency I am going to do here, resolution and convenience of use. Comparing between the eye and the CCD. They love the examiners, eh? How convenient is an eye? That's pretty convenient, isn't it? Anyway, we'll look at how convenient CCDs are in comparison to that. And just as a warning here, no knowledge of the structure of CCD is required. I'm going to show you a little bit about how they work because it's actually very difficult to describe if you don't see the work. And there's our 3 learning objectives at the bottom. So get your notes out, get you ready. Pause this video here. You need to be able to write those 3 down there. And put the date in the top right hand corner to make sure you know when this was. This video is not going to be very long. I'm going to be pausing it to make sure you can catch up. So this is really an intro to looking at everything else to do with telescopes apart from the angular resolution, which we did last time. Let's crack on. So we're going to be looking at detecting all types of electromagnetic radiation. That's what I mean by EM. This rather complicated diagram over here to the left here tells you a little bit about the spectrum. The spectrum goes this way, and this is radio up here and X-ray at the bottom here, and it tells you all about the different telescopes, and you can see these lovely telescopes all in here. James Webb Telescope, they're still under commissioning at the moment. Let's hope it does actually get going. There's Hubble Space Telescope now. I'm going to be talking about a few of these, but you can go and look on the internet to see all the more details of them. It's a fantastic piece of technology. And also, we're just going to look at comparing it and the modifications of each of the telescopes. We'll look at the different wavelengths as well. And I'm going to leave you a little project to be able to look up how these things actually work, like the XMM, the X-ray telescope. In a second. So this is the view of the Milky Way. Not invisible. This is in infrared. So if you look at this across the sky, you can see the central parts of the galaxy are incredibly bright infrared. That's because there's lots of dust emitting, very cool dust. When I say cool, I mean really cool. It's sort of a few hundred K. That means a lot cooler than any stars. You can see these little dots out here, little dots of cooler dust, not stars, but giving out little dust areas. Sometimes they're large, sometimes small. Chandra is a type of X-ray telescope, and this is a supernova remnant. This is the false colours in here, of course, and these are all X-rays. So these are different hard X-rays and soft X-rays, which are high energy and low energy X-ray called X-ray emission. This is the sun in UV. UV is not blue, by the way. It's just false color again. But this is what it looks like. Very similar to what the looks like in the visible. If you take a visible picture of the sun, and you can see the different areas of high amounts of emission compared to lower amounts of emission. But it's all relative. It's all pretty warm down there. About 6,000 K is the surface. And this is visible of the sun. What's great about this, of course, you can see these sunspots. And these are areas of north and south magnetic poles. These are big magnetic loops that come out of the sun here. And these sunspots puzzled many people. And that's what it looks like. Now, Jupiter, of course, you can look at it in the infrared. It looks very different. You can see the big red spot there, big storm raging. But this is an infrared observation of Jupiter, and it can tell you lots about the different gases and the different temperatures that are going on. And this is a picture close to my heart. This is the first picture of using the scuba telescope on the JCMT about 20 odd years ago, and this is one of the first pictures that showed that there was an awful lot of dust out there, because this is the dust emission from galaxies many miles away, so large redshifts, large distances away, and believe it or not, each one of those purple blobs is actually a galaxy. It's not very pretty, but submarine astronomy never is. This is a radio observation of M82, which is a large galaxy, not too far away. Merlin is and VLA, these are two types of radio telescopes, and this used a large array of radio telescopes around the world to produce these different radio sources. You can see the galaxy there, and the individual radio sources kicking out an awful lot of radio wavelengths. And it all boils down to this thing in here. That little thing down there in the middle there is a CCD, charge coupled device. It's a very small chip, and if you've got your mobile phone handy, like I have here, the mobile phone eye says, there it is, right in there. That is basically a zoom in into the camera on your mobile phone. Really, really small, very, very small, less than a millimeter across, and the technology is just better and better. How do they work? Well, basically you have a series of small chips inside, and each of those chips is associated with a color. The light enters the lens, it goes into a single pixel, which is what a pixel, a little tiny bucket, and then it builds up charge. The light is a proportional to the charge, so light goes in, it causes a little electron to go and do its thing, and then more electrons, more charge, more voltage, and then that can be represented in an image on the front of your mobile phone or on a piece of software that's attached to a massive telescope. They both work the same. And of course you get three different colours, red, green, blue. You put them all together and you get a lovely colour. You don't really have to know these work, and I can see the examiners why. That's how they do work on the bottom right there. As you can see, it's pretty flipping complicated, but really this is probably about as good as it gets. All the photons come in, they go into a bucket, and the bucket gets poured into a bigger bucket, and then you measure how much is coming out of one part of it. The key to this is quantum efficiency. Now, quantum efficiency is how many charge carriers, usually electrons, are produced compared to how many photons, particles of light, that come in from space. So if you've got a very high percentage, that means you've got lots of electrons being produced for lots of photons, which is good. A bad quantum efficiency, which would be 1%, is that only 1/100th of the photons was actually converted into an electron or a charge carrier. So that's poor. But CCDs have quantum efficiencies around 70 to 80%. Some are larger, some are smaller, but it's pretty good. So that means it's almost catching all of the photons that are coming in. Very sensitive, and that's what we want. The eye, not pretty good though. And this is the process. So basically, you have the structure, you have a silicon chip, divided picture elements, they've got little pixels, sort of divided up into a little grid. The photons come in, electrons are released, the electrons are liberated, they trapped in potential wells effectively, and then that electron pattern gets built up, because you can see how much charge is compared to other places. You get lots of electrons, bright, not some electrons, dim, and you put that onto an image, and lo and behold, you get the images that we have on our mobile phones. Quantum efficiency per pixel, 7%. Now, the AQA people would like you to be able to compare a CCD to an eye. What I showed you before, of course, is the detail of it, but I can't really describe what it is before. It's a shame. My head is in the way down here, but I'll tell you what it says. So here's your eye. Quantum efficiency, 1%. Resolving power. Now this is always difficult, because if it's a naked eye, your resolving power is about an arc minute, which means 1/60th of a degree. And if you don't like that, then it's about 0.02 degrees, or 0.0003 of a radian. Again, it doesn't really give you much help in terms of real world. This is probably a better one, which is 0.3 meters, 30 centimeters at a kilometer. So you can see something that's 30 centimeters high at a kilometer. Somebody also described it as 5p at the end of a football pitch, which I think is probably a good one. So if somebody held up a 5p, you could probably work out what they were holding. In other words, you could see their fingers were apart and something silvery. And of course, you can't get much more convenient than something stuck inside your own head. So therefore, you can have, but there's no recording yet. However, CCDs, of course, 78%. Resolving power, 10 to the -8, which is probably the best resolving power you're going to get on the size of the telescopes that we've been talking about so far. That's in radians, by the way, so you can see compared to 10 to the power of -3, -4 for an eye. But to -8, that is thousands of times better than the eye. Not so convenient, you don't have one stuck to your head yet. They're processable, which means that you can add images together and also can communicate them. That's what it says behind my head, which is means that you can send them to other people. So in other words, CCDs, they kind of win hands down. So we talked about the different wavelengths at the start. So these are the different wavelengths. I'm going to rattle through them. Specifications are a bit ambiguous because in the title and the specification it mentions all these different types of telescopes, but actually in the specification text it only mentions a couple of different types like radio and optical. Compare it, but I'm going to do them all. I don't think the examiners really realise that. They may have done that on a Friday afternoon. So these different telescopes here, some in space, some on ground, some buried into the ground, and others in sort of arrays, all sort of lined up. So why bother? So I'm going to explain the designs of non-optical telescopes, and then explain why the atmosphere and humans limit ground-based observations. In other words, how can we make them as good? So if we look at the sky, we only get a certain amount of electromagnetic radiation coming down. Now I've just taken a little slither here from UV up to infrared, nearly into microwave, but not quite. I did this because otherwise it starts getting a bit complicated. The passbands are very narrow. Now passband basically means that I can observe here, so this is the amount of percentage of energy arriving at sea level. So you can see I've got a good eye on the sky at about 1.3 micrometers, 10 to the minus 6. But you can see that it drops off into UV quite quickly, and that's the ozone layer, of course, absorbing, and that's O3, that's what it says here, the ozone layer absorbing quite a lot of the UV here. And you can see there's absolutely nothing getting through at 1.5, and again here, and again here. Now, a lot of these refer to the absorption of certain molecules in the atmosphere, like water vapor, CO2, different parts like that. So in other words, they absorb these different parts. So there's only certain wavelengths we can observe. And if you get to gamma ray and X-ray, you really are getting quite difficult. It's difficult to observe X-rays and gamma rays. You think that gamma rays and X-rays would get straight through the atmosphere. The atmosphere is pretty thick to gamma rays and X-rays. Radio is fine. There is other problems with that, which we'll come on to in a second. They're usually human related. But you can see that we've got certain limitations. So here we are. We got radio. So radio observations is a dish, and you'll recognise these. And it's exactly the same as a Cassegrain. Light comes in, it gets reflected up to a convex secondary, and then goes back down straight through the centre of the telescope here, down to some sort of amplifier, and then it records it. So why bother with these multiple arrays here? Now, the problem with the radio, of course, is your diameter here has to be big. Why does it have to be big? Because your wavelength is big, and to get your angular resolution, your theta here, your lambda, which is sometimes in kilometers for radio, and most of the time it's in centimeters, your diameter's got to be huge to get this number small, because you want that number small. And so therefore you've got to try and get that. Now, often the examiners in AQA won't give you wavelength, they'll give you in hertz. So here we are, I've got 50 gigahertz here. And so therefore you may get asked, how do you produce 10 to the minus 8 resolution with 50 gigahertz observations of the sky? And then you've got to calculate diameter. Of course, that diameter is going to be enormous. And that's why you have multiple radio telescopes. And those multiple radio telescopes then give you a much wider diameter. It's not the full diameter. It's not, because there's bits obviously missing because you haven't got one entire dish. But nevertheless, it still works. And there's something called interferometry as well, which does help in the resolution, but that's not part of the AQA spectrum. We're going to look at interferometry. It's fascinating. The VLA, very large array. Astronomers love giving the names. Creative names, you can tell. Very large arrays, the name of that telescope, you can see there. Now, the collecting area goes as the square of the diameter. Now, in A-level world, it's just proportional. So in other words, you just have to remember that the collecting area goes as the square of the diameter. So if you're asked to compare two telescopes, this is a meter, this is 2 meters. You have got 1 squared, 1, and you've got 2 squared, 4. You've got 4 times the collecting area in a 2-meter telescope compared to a 1-meter telescope. And the examiners will only ever ask you to compare 2 telescopes. They won't ask you to actually calculate the area. Well, he says they may do, but I've never seen them yet. So we'll see. Now, if you go to a nice place like Mauna Kea here, this is the James Clerk Maxwell telescope. It's now defunct. This is quite an old picture. And this is the Caltech Submillimeter Astronomy down here. They're replacing these old telescopes here with these sorts of things, which is arrays of microwave telescopes. And this here is a small millimeter array, which is just built at the back here. on the top of Mauna Kea, which is on the Big Island of Hawaii in the middle of the Pacific. And there's reasons why it's on the top of a volcano in the middle of the Pacific. It's dry. And with dry, remember when I showed you those pass bands, the drier it is, the clearer the sky is. Now, I don't mean clouds billowing across the top, which can be a problem. But in this case, it's dry. In other words, the atmospheric water vapor, the humidity is very low. And they need to be high as well. Get them high, you get less atmosphere, so you get less absorption. So high and dry is brilliant for any sort of observing at all. And of course, being in the middle of the Pacific, it also has an extremely good opportunity to get away from as much light pollution as possible as well. Because you've got the light Big Island, there is a population there, a very small population, live around the outside. This is many miles away from civilization. So therefore you can get a dark, high and dry. Why is it dark? Light pollution. Why is it high? Your atmosphere is much thinner, therefore you get less absorption. Why is it dry? Your water vapor level is lower, so therefore you get less absorption as well. There's your argument. And of course, then you can stuff things in space. So if you want a submillimeter telescope, which is the one I worked on, for one reason, there you go, just to prove I'm not lying. There you go, there's my name. I worked on this in a very minor role, I must say, and we are on the Spire camera, which is a submillimeter camera that went on Herschel, a 4-meter telescope that went up into space. Now it doesn't work anymore. But nevertheless, it went up there and did that. Of course, the best thing to do, go into space. Problem is, of course, telescopes are much smaller. You can't get a 15-meter telescope into space easily. That was a 4-meter. That was the biggest space telescope that was done at the time, and now, of course, it's been shrunk by James Webb. Infrared telescopes like this one, which is the old UKERT, on Earth, of course, it's difficult because you've got to go through certain passages. That's why putting something in space, like the Hubble Space Telescope, you can immediately see all the telescopes. You can see UV, for instance. There you go. There's a UV picture taken by the Hubble Space Telescope, and here's a picture of the Hubble Deep Field, which is a very, very dark area of the sky. Again, taken from UV all the way to infrared. So going into space, you avoid the absorption of the atmosphere. You avoid the absorption by water vapor. Water vapors as well, of course, it's pretty dark in space, and you can observe all day, every day. You don't have to wait for that thing called night. Although in terms of radio telescope, they don't care about night, but for the other ones, it can be important. And then when you go to the other end of the spectrum, X-ray, you've got Chandra X-rays observatory. You don't really have a mirror, you have these things called grazing mirrors, which sort of pull in the photons, and then you get to see things like black hole accretion disks, which is what that blue thing is there. This is a black hole destroying a nearby star. These are sort of artist's impression here. You don't really see the radio. This is radio emission coming out here. What you will see, well, okay, there's some optical emission as well, but it's nowhere near as strong as this. And therefore you get accretion disk, which is basically a plug hole effect of all the matter going into it. Pretty dramatic. This is what you need to be able to do. So in the specification, it says similarities and differences of radio telescopes compared to optical telescopes. But what I said before here, notice it's got infrared, UV, and X-ray telescopes up here. Not quite sure why they did that, but nevertheless, that's why I told you about those others. Discussions could include structure, so in other words, how big it is. You can make them very big because you can make them very thin as well, and they're a reflecting telescope, of course, because therefore you don't have to support as much weight. Positioning, high, dry, or in space. Use, what objects are we looking at, which I've mentioned before, and together with comparisons of resolving and collecting power. Resolving power, lambda over d, so wavelength of the diameter. Collecting power, just referring to d squared. So all of those things you need to factor in to this. Now, I've given you a clip of the fantastic AQA resource, which is a booklet that was made by Mr. Organ. I love his name. It's not quite up to date, but nevertheless, it still works. You can get hold of that, and this is all the information that's on there. Really good resource. So thank you, Mr. Organ, or Dr. Organ, not quite sure. And this is the kind of question you're going to get. The International Ultraviolet Explorer and the Gran Telescopio Canaris are two examples of reflecting telescopes. And there's a table. So the IUE is 0.45. It's in orbit. It's an ultraviolet telescope, and its typical wavelength is about 2 times 10⁻⁻⁷, so about 200 nanometers. The one in the Canary Islands, the GTC, 10.4 meters, Earth's surface, but it's above sea level, quite a long way above sea level. Visible infrared, and there you go. It's about 1,000 nanometers. That's infrared. Compare the two telescopes in terms of location, collecting power, and minimum angular resolution. So as you can see, everything I've done so far ticks these boxes. So first of all, location. In orbit, you've got to mention about absorption of the atmosphere, you've got to mention about the lack of absorption of water vapor as well, and also about light pollution. Compare those two. Now, the fact that it's given you 2,300 meters must mean that you are above sea level, so therefore the atmosphere is slightly thinner and slightly drier as you would go above. So therefore you're ticking those boxes as well. Collecting power, it's d squared. So what you're going to do is compare and get the ratio. When people say compare, they always mean do a ratio. So that means 0.45 squared divided by 10.4 squared. And then what that number is the comparison. How many times better is the collection area of the GTC compared to the IUE? So when the word compare it means do a ratio, or at least compare how good or bad compare it is. If it's numbers, do a ratio. Minimum angular resolution. Now, this is where we, again, do a minimum angular resolution. So lambda over d, so let's find the wavelengths. There they are at the bottom. There's your wavelengths. And then your diameter. So this number divided by this number will give you the minimum angular resolution, Rayleigh criterion, compared to that number divided by that number. Now, of course, once you've got those two minimum angular resolutions, you divide one by the other and say how many times better it is compared to the other. So pause the video, do all those calculations, satisfy yourself, and then I'm going to reveal the answers in 3, 2, 1. There we go. So you want to pause the video there to have a good look at see what your numbers. So GTC was 5 times better at resolving. GTC was 530 times the collecting power. And of course, you've mentioned about those as well. So pause that if you want to have a good look at that. And that's the signal. Now, I'm going to give you a bit of a task here, because obviously that was just a UV and infrared telescope. You've got to know about the other ones. And radio, microwave, infrared, UV, and X-ray are the ones that are mentioned in the top of that AQA specification. So go and have a look, go and have a cruise around the internet. Find one telescope for each of these, give an example, and importantly, I think the objects of interest here, it doesn't mention the specification, but why do we build these things? Why do we spend billions building these things? The whole point of doing A-level is not to just get an A-level, it's to work out what on earth we're doing as humans. And there you go. And as humans, we're looking at the most incredible things in the universe. And go and look at what they are. And I've mentioned a few here, but go and find out. It's fascinating. You'll want to be an astrophysicist as well. It's brilliant. So, one last little question. This is going back to what we were talking about before. Spacecraft passes Pluto at a distance of 12,500 kilometers. Kilometers. Always look for units in these things. Is that going to be relevant? May not be, but you never know. A telescope on board has an aperture of diameter 0.21 meters. We'll find that operates at a wavelength of 450 nanometers. Could be okay there as well. Discuss whether the telescope is suitable for studying a crater with diameter of approximately 1 kilometer on Pluto. So, straightforward question. Find the angular size of the crater, compare it to the angular resolution of the telescope. Angular size there, it's cut off behind me, but it's actual size divided by distance of object. So this is the, I'll put this picture in here, by the way, just to help you. It's nothing to do with this. This picture didn't come with this question. I'm just putting it in there. So your angular size is always the size of the actual object. So in this case, it's 1 kilometer. This is a galaxy I've got here, but it's a crater. So this will be 1 kilometer. This will be 12,500. And then, of course, your angular resolution, which is theta equals lambda over d. Theta, of course, is what we want. Lambda is this one, so 450 times 10 to the power minus 9, because it's nanometers, divided by your diameter. And compare those two. 3 marks, great, and then work out, is it big? In this case, it is, because my angular resolution is 40 times smaller than my size of the crater, which means I can get basically 40 angular resolution units within it, which means I can work out detail. Not a great deal of detail, but nevertheless I can still get it. Pause if you want to do the actual calculation now. And I'll show the answers in 3, 2, 1. And there it is. Now, personally, I always do the angular resolution and then calculate the size and then work out the ratio between them. They've done this thing where they calculate the resolution, then multiply it by the distance away from it. Frankly, I don't think that helps. 27 meters. I don't think that helps. Personally, I prefer this bit over here. Find the angle subtended by a 1 minute crater, do that, and then compare it to the angle. Do that, and then you've got two angles to compare to. Is one bigger than the other? Yes, it is. Much easier. It makes more sense to me anyway. You may disagree, but for me, it makes more sense. So that's it for this particular one, comparing telescopes, different wavelengths and different locations. A lot to take in. Quite a long bit of learning for you there, but nevertheless, it's a complete part. This is probably, I put it as just one lesson, but you can do that lesson. And my phone is ringing just at the right moment.